When we look up at the night sky, we often feel a quiet comfort. The stars seem eternal, predictable, peaceful. When we plan satellite launches, we assume Earth's orbit is stable and safe. When the tides rise and fall each day, we trust that the moon's gentle pull will always guide the oceans. When astronomers scan deep space, they expect the cosmic dangers they find to be incredibly far away. But what if, one day, a strange object drifted into our solar system? What if it was small, silent, invisible, and yet held the power to tear our world apart? What if a primordial black hole, no bigger than a mountain, no wider than an atom, slowly approached Earth? What happens first? When would we know? How would the sky change? And at what moment would humanity understand that something was terribly wrong? A black hole near Earth sounds like pure science fiction. But astrophysicists seriously consider the possibility of tiny black holes wandering through the galaxy, left over from the birth of the universe. So the real question becomes, if one drifted too close, what would happen to us, step by step? Open your mind. Follow your curiosity. Welcome to the Center for Curiosity. Before we imagine a black hole approaching Earth, we must first understand what actually is a black hole. Here's the simplest way to look at it. A black hole is not a hole. It's not an object you can touch, and it's definitely not an empty doorway in space. A black hole is a place where matter has been crushed into such a tiny space that gravity becomes unbelievably strong. Let's break that down. Imagine taking something the size of a mountain and squeezing it until it becomes smaller than a grain of sand. The gravity created by that extreme compression becomes powerful enough that nothing, not even light, can escape. This boundary is called the event horizon, meaning once something crosses it, it cannot come back. But our scenario involves a special kind of black hole, a primordial black hole, supposedly formed right after the Big Bang, potentially as small as an atom, but with enormous mass. They don't suck things in like cosmic vacuum cleaners. Instead, they behave like super compact, super heavy objects. If one passed near Earth, its gravity, not its suction, would be the danger. To understand the timeline of destruction, we first need to know how gravity spreads. Gravity becomes weaker with distance, extremely weaker. So, at first, everything would seem normal. The idea of primordial black holes began in the 1970s. Physicists wondered, if the early universe was chaotic and uneven, could some regions have collapsed into tiny black holes? This wasn't fantasy. It was a serious question raised by Stephen Hawking and others. They proposed that these black holes could have survived until today, drifting silently through space. But why didn't astronomers detect them? Because primordial black holes are small. Some might be the size of a proton, some the size of a marble, some the size of a mountain but compressed into a microscopic point. They emit almost no light. They do not glow unless they consume matter. They do not behave like stars, planets, or asteroids. In history, every time astronomers thought they found something mysterious, unexpected gravitational effects, strange orbits, unexplained motions. They briefly wondered if a primordial black hole was involved. But none have been proven. Still, the idea remains possible, because the laws of physics do not forbid their existence. So now, let's place one into our solar system. Now begins the cinematic scenario. We will imagine a primordial black hole, roughly the mass of a large mountain. Too small to see, too dark to detect visually, but massive enough to disrupt Earth if it comes close. At first, nothing seems unusual. The black hole drifts through the outer solar system, passing the orbit of Neptune. It is moving fast, tens of thousands of kilometers per hour. No light, no heat, no radio signal. Only gravity. Astronomers studying long-period comets might notice something odd. Comets that should orbit predictably start behaving strangely. Their trajectories bend slightly, as if tugged by a ghost. But Earth has no reason to worry yet. As the black hole moves inward, icy bodies in the Kuiper belt shift. Some accelerate, some collide. A few plunge toward the inner solar system. Astronomers would detect this chaos and know something massive is interfering, but they wouldn't know what. Was it a rogue planet? A clump of dark matter? A mistake in the data? Subtle warning signs begin. Probes like Voyager, New Horizons, or deep space satellites begin drifting off course. Navigation corrections become more frequent. Engineers notice something out there is pulling on them. This is humanity's first true warning. Nothing dramatic, but measurable. Gravity spreads far. Even a small primordial black hole influences the solar system. Astronomers now know there is an intruder. Not big enough to destroy planets outright, but big enough to cause trouble. When it reaches the inner solar system, effects become obvious. Mars' orbit bends slightly. Its moons wobble. Dust storms behave strangely, stretched by small tidal forces. Earth still feels nothing, but astronomers are now certain this is a compact, invisible, massive object. Now the real timeline begins. The black hole approaches Earth's orbit. First effect, satellites. Their orbits depend on precise balance. A slight gravitational disturbance can ruin that balance. One by one, some satellites drift off course. GPS becomes unreliable. Weather satellites need constant correction. Astronomers announce an emergency. Something is altering Earth's orbital environment, but no one can see it. When the black hole gets within a few million kilometers from Earth, Earth feels its gravity. Not enough to destroy anything yet, but enough to alter tides. Low tides become lower. High tides become slightly higher. Patterns shift unpredictably. Coastal scientists report anomalies that cannot be blamed on the moon. Oceanographers realize something else is pulling the oceans. Not visible to the naked eye at first, but telescopes detect tiny gravitational lensing. Stars near the black hole's background position appear warped, just slightly, like looking through a curved piece of glass. This is the moment humanity realizes a black hole is passing near Earth. This is the critical stage. A primordial black hole mass behaves like a heavy object. If it passes far away, Earth survives. If it comes close enough, the timeline grows catastrophic. Let's explore the dangerous scenario. The black hole passes within 1 million kilometers from Earth, about 2.5 times the distance to the Moon. Here's what happens next. Gravity doesn't just pull oceans, it pulls rock. Subtle at first, invisible, but building. Volcanic activity increases. Fault lines strain. Small earthquakes become more frequent. This is not fantasy. Tidal forces shape moons and planets throughout our solar system. If a small black hole comes close, the same thing happens here. Air is mass, and mass feels gravity. Wind patterns shift. Jet streams bend. Storms behave unpredictably, forming in unusual locations. Meteorologists issue warnings they cannot fully explain. Gravity from the black hole begins tugging satellites downward. Some burn up in the atmosphere. The ISS requires continuous boosting to avoid crashing. Space becomes chaotic. Communication networks begin to fail. This is the doomsday zone, within 300,000 kilometers, the distance to the Moon. Here, the black hole's gravity competes with the Moon's gravity. Tides could rise dozens of meters. Coastal cities flood. Bridges collapse under dynamic stress. Earthquakes increase. Volcanoes erupt globally. Crustal plates shift unpredictably. The planet does not break apart, but civilization does. If, by terrible luck, the black hole passes even closer, tens of thousands of kilometers, Earth is torn by tidal forces. Oceans lift into massive walls of water. Entire continents flex. Satellites rain from the sky. The planet's orbit itself may destabilize. If the black hole passed directly through Earth, which is theoretically possible given its microscopic size, it would drill a destructive tunnel as it goes. Matter vaporizes. Shock waves circle the globe. Earth would not explode, but it would be devastated beyond recovery. But reality is not always apocalyptic. Here are important nuances. Exception 1. If the black hole passes farther away. If it stays several million kilometers distant, Earth experiences only strange tides, satellite disruptions, minor orbital changes, unusual auroras, and sky distortions. Life continues. Civilization recovers. Exception 2. If its trajectory misses Earth by a wide margin. Like a heavy asteroid, it may simply curve around the Sun and leave. Earth would experience a bizarre astronomical event and nothing more. Exception 3. Radiation is minimal. Primordial black holes do not emit radiation unless actively consuming matter, so the danger is almost entirely gravitational. Exception 4. Detection may happen very late. Because it is invisible, astronomers might only identify its presence after major gravitational anomalies. Here's the mind-bending part. The same physics that makes a black hole terrifying also makes it surprisingly predictable. Gravity obeys strict rules. If we detect the object early enough, we can calculate its path precisely. But here's the twist. A primordial black hole barely interacts with anything. It could pass through Earth, through the Moon, even through the Sun, and emerge almost unchanged. It is not malicious. It does not hunt planets. It simply travels along a cosmic trajectory set billions of years ago. The deeper truth is this. Earth is fragile, not because black holes are common, but because gravity is universal. A small object, tiny, invisible, silent, could reshape the entire solar system if its mass were compact enough. Why does this matter today? Because studying small black holes helps scientists understand dark matter possibilities, early universe conditions, the limits of gravity, and how to detect invisible massive objects. It also teaches civilization humility. We build satellites, cities, networks, and global systems, assuming the universe is predictable. But cosmic events, however unlikely, remind us how delicate our environment truly is. Understanding this scenario prepares humanity for unexpected gravitational anomalies, the need for early warning systems, improved space observation networks, and, most importantly, it helps us appreciate the miracle of living in a stable, calm corner of the galaxy. Today, we explored what would happen if a small, primordial black hole approached Earth. We learned what black holes really are, how primordial black holes could form, how a wandering one might enter the solar system, how astronomers would detect it, how satellites, tides, weather, and crust would respond, the possible catastrophic outcomes, and the rare but real scientific complexities involved. We followed a timeline from everything seems normal to the solar system begins to wobble to Earth faces escalating gravitational stress. Understanding this scenario shows us both the power of gravity and the fragile beauty of our world. So the next time you look at the night sky, or check your GPS, or watch the tides roll in and out, you'll know exactly how these everyday experiences would change if a tiny, ancient black hole ever wandered too close. The comfort of the stars, the stability of satellites, the rhythm of the oceans, all depend on the delicate balance of cosmic gravity. If a black hole passing near Earth could cause so much chaos, then here's a question for you. What would happen if two primordial black holes collided near our solar system? If you enjoyed this explanation, consider subscribing for more curiosity-driven content.